Topic 3, Thermal Physics 3.1 Thermal Concepts. Molecular theory of solid, liquid, and gas. There are three phases of matter: solid, liquid, and gas. In solid, molecules can only vibrate, they cannot translate. They vibrate in a fixed position, but they cannot move around. In a liquid, the molecules can vibrate and move about freely in a fixed volume. In going from a solid to liquid and in melting, some of the intermolecular bonds are broken, giving the molecule more freedom of motion. In going from a liquid to gas, evaporation or boiling, some of the intermolecular bonds are broken. Phase change. The process of going from a solid to liquid is called melting, and the process of going from a liquid to gas is called boiling. Each process can be reversed. Let's take a look at the phase change process and examples. Solid to liquid, melting, example is ice to water. Liquid to solid is freezing, reverse. Water to ice. From liquid to gas, boiling. Examples: water to steam, gas to liquid is condensing, steam to droplets. Solid to gas, sublimation, frost evaporation, example. And gas to solid, deposition, an example is frost. Internal energy. All substances are composed of individual molecules that are in vibration. As we heat up a substance, its vibrations becomes more energetic. This is an increase in kinetic energy of molecules. Simultaneously, as heat is being added, the molecules are also moving further apart. This is an increase in potential energy of the substances. Two energies together are called internal energy of substance. So the internal energy is a sum of the kinetic energy and a potential energy of the molecules. When thermal energy or heat is added to substance, it is stored as internal energy. So internal energy is a sum of the kinetic and potential energy of the molecules. Total internal energy can be kinetic energy due to vibration and translation. Thermometer measures the internal kinetic energy. Temperature is a measure of the average kinetic energy. Potential energy due to intermolecular forces. Think of Hooke's law, F equal to minus kx, and phase change. Yes, so lower one is a lower potential energy and upper one is a higher potential energy. When gas is heated in an enclosed space, its pressure P increase. We have the following experiment plots pressure versus temperature T in Celsius. So the y-axis is in pressure and x-axis in temperature in degrees Celsius, not Kelvin. We can extrapolate the graph like this. Now we repeat using different gases. So we can observe a very interesting trend here. The lowest pressure P that can exist is 0. Surprisingly, the temperature at which any gas attains a pressure of 0 is the same, regardless of the gas. The Celsius temperature at which pressure is 0 is minus 273 degrees Celsius, or precisely minus 273.15 degrees Celsius. Because the lowest pressure that can exist is 0, this temperature is the lowest temperature that can exist, and it's called absolute 0. We have a new temperature scale that has absolute 0 as its lowest value, is called Kelvin temperature scale. The right side in Kelvin and the left side in degrees Celsius. Absolute 0, freezing. So minus 270 degrees Celsius is equals to 0 Kelvin, and 0 degrees Celsius is equal to 273 Kelvin. So we have the relationship between Kelvin and the Celsius scale is given there. Temperature in Kelvin equals to temperature in degrees Celsius plus 273. Conversion: convert 100 degrees Celsius to Kelvin and 100 Kelvin to degrees Celsius. So let's convert 100 degrees Celsius. We just plug in temperature in Kelvin equals to temperature in degrees Celsius plus 273, which is 100 plus 273. So that is 373 Kelvin. So 100 degrees Celsius equals to 373 Kelvin. Similarly, we convert 100 Kelvin to degrees Celsius. So 100 Kelvin equals to temperature in degrees Celsius plus 273, and temperature equals to minus 173 degrees Celsius. So 100 Kelvin equals to minus 173 degrees Celsius. Specific heat capacity: different materials absorb heat energy in different ways. This means that if we have two different substances having the same mass and each absorbs the same amount of heat, the increase in temperature may be different. So let's have two different substances. They have the same mass and they absorb the same amount of energy, but the increment in temperature may be different. We define the specific heat capacity, C, of a substance as the amount of heat or thermal energy needed per unit temperature increase per unit mass. So Q equals to mc delta T. Each material has its own unique value for C. So Q is the thermal energy, M is the mass, C is the specific heat capacity, delta T is the change in temperature. Air has density of about Rho 1.2 kilogram per cubic meter. How much heat in joule is needed to raise the temperature of the air in 3 times 4 times 5 meter room by 5 degrees Celsius? Specific heat capacity of the air is equals to 1050 joule per kilogram per degree Celsius. The change in temperature is equals to delta T is 5 degrees Celsius. This is change in. So change in can be degrees Celsius or Kelvin. Mass, we get the mass from the density formula. Density equals to mass over volume, and mass equals to density times volume. Density is 1.2, volume is 3 times 4 times 5. That is 72 kilogram. So how much heat or thermal energy is needed to raise the temperature of the air in? So the thermal energy is needed is Q equals to mc delta T. Mass is 72, specific heat capacity of the air is 1050, and a change in temperature is 5. That gives us 378,000 joule or 380 kilojoule. Suppose we have 200 kilogram steel ingot and 200 kilogram block of wood, both at room temperature, which is 20 degrees Celsius. If we add 1,143,000 joule of heat, the energy of a Snickers bar, to each object, what will its final temperature be? Specific heat capacity of the steel is 460 joule per kilogram per degree Celsius, and the specific heat capacity of the wood is 1680 joule per kilogram per degree Celsius. For both, we have a Q equal to mc delta T as they are changing temperatures. So Q equal to mc delta T, and the higher temperature minus the lower temperature. So for steel, energy added is 1,143,000 equals to mass is 200, and the specific heat capacity of the steel is 460, and temperature, final temperature minus the initial temperature 20. Solve this, we get T equals to 32.4 degrees Celsius. So the temperature from 20 increased to 32.4 degrees Celsius. For wood, we apply the similar. The heat added is 1,143,000 equals to same mass 200, but a specific heat capacity is different. So that is 1,680, and final temperature minus initial temperature 20. And solve it, we get 23.4 degrees Celsius. So we provide same amount of energy to two different substances. They have the same mass, but wood has a higher specific heat capacity, but the change in temperature is very small, only 3.4 degrees Celsius, while the steel has a lower specific heat capacity, 460, but the change in temperature is much higher, 12.4 degrees Celsius. Sketching and interpreting phase change graph. Suppose a thermometer is frozen in ice, and the ice is further cooled to a temperature of minus 20 degrees Celsius. We slowly add heat and plot the temperature versus the heat added. Right now, look at the diagram. We are providing thermal energy, and ice is frozen at minus 20 degrees Celsius. Look at temperature increase from minus 20 to 0. Now we are supplying energy, but the temperature remain at 0 until all ice is melted. Yes, temperature still remains 0 degrees Celsius until all the ice are melted. Yeah, all the ice are melted right now. Now the temperature start to increase, and it's increasing from 0 to 100, and we are still supplying energy, but the temperature remain at 100 degrees Celsius until all the water evaporated. Now temperature start rising again. So we have ice at minus 20, temperature rising, and then melting and turn into water, and temperature of the water is rising at 100 degrees Celsius, start boiling, but temperature remain constant, and then turn into steam. Since the thermometer measures the kinetic energy, and since the temperature doesn't change during the phase change, the heat must be getting stored only as a potential energy during phase change. So if you look at the graph and also our animation, during phase change we supply a thermal energy. During melting and boiling, the temperature does not change. The heat we supplied must be stored as a potential energy. Internal energy is the sum of the kinetic energy and the potential energy. That is all the process. And the kinetic energy is linked to change in temperature. So this part we have a kinetic energy, this part change in temperature, we have kinetic energy, and also this part we have a change in temperature, we have a kinetic energy. Potential energy happens during phase change. So let's take a look at phase change in terms of molecular behavior. As a model to help explain phase change, consider a molecule in an open box which can move left and right but must remain captured in the box. As more heat is stored as potential energy, the particle in our model gain height. Finally, the potential energy is great enough to break the intermolecular bonds and change the phase of the substance. And the molecule is free now.